Hello everyone, and welcome to this session where I will try to help you understand how to utilize the program called Ftool to analyze the statically indeterminate beam shown in the figure on screen. After performing structural analysis of the beam, I will ask the program to draw its shear force and bending moment diagrams, as well as its deformed shape. Please let me point out at the beginning that general finite element packages and programs that use the stiffness method of analysis do not distinguish between statically determinate or indeterminate structures. The solution procedure is the same for both. Furthermore, the words static and kinematic are used when we refer to the solution performed using the force, also known as flexibility method, and the displacement, also known as the stiffness method, respectively. Static is used with the force methods where the unknowns are forces, and kinematic is used with the displacement methods where the unknowns are deformations, where the latter is universally referred to as degrees of freedom. While you are studying, you should always practice solving your examples by hand. Once you are done with the hand solution, you can use a computer software to check the correctness of your solution and to enhance your computer skills. Now, why Ftool in particular? Because it is a very straightforward program to download and use. Let's say that you are a civil engineering student at a stage where you have completed your first structural analysis course, and now you will be taking your second one. This is a good time for you to start using a computer tool to perform structural analysis. Later on, when you take your advanced or elective courses, you will be introduced to other international packages of structural analysis and design, and in some advanced courses you will be asked to develop subroutines that will perform structural analysis of different kinds of members. Let's get started. Again, we will be analyzing this statically indeterminate beam that is 12 meters long with a 50 kilonewton load located at midspan. The support at A is fixed and the support at B is a roller. We are given the modulus of elasticity of the beam as well as its moment of inertia. The minute you open the program Ftool, go to File, Sign Convention, and add a tick next to plot diagram values on the compression side of member. In order to be compatible with the textbooks that we are using, click Apply. Then we go to Options. I like to set all text sizes to large so that the text can be displayed in a clear fashion. So I'm going to choose large here. Again, I'm going to choose large and large. I'm going to click on options again and go to units and number formatting. Remember that the beam that we are analyzing is using the standard international system of units. Therefore, I'm going to go here and select standard international. In addition, I'm going to ask the program Ftool to show me the forces with 3 decimals and the moments in 3 decimals. Next, we want to add our beam segments. Note that we have a concentrated load located at midspan, and therefore I'm going to draw this beam, which is 12 meters long, using 2 segments. One will start at 0 and end at 6. The other will start at 6 and end at 12, so that I will be able to place this 50 kilonewton over a node. In order to do so, we can use 4 different methods in Ftool. The first one, I'm going to activate the grid here along with the snap tool, and I'm going to insert nodes by clicking at the points on the grid. For example, if I start here, which is 0, 0, you can go here and see the coordinates of each of these nodes on the grid, X and Y. So if I come close to this point, the snap tool will bring me right at it, and you will see that the coordinates here are 0 and 0. I'm going to place my first node. I'm going to walk away here to the right 6 meters and place another node, and I'm gonna walk away again to the right till I reach here in the X coordinate 12, and click again to have my third node. Now I can click on Insert Members and ask the program to add a member between the first node and the second node, again between the second node and the third node. This way we have a beam that is 12 meters long and is made of 2 segments. This is one way of doing it. I'm gonna click on the select mode and select everything here and delete it. Another way of doing this is by clicking directly on Insert Members and asking the program to draw members directly between 2 nodes representing the start and the end of each beam segment. So I can tell Ftool, draw a beam that starts here at the origin all the way to 6 meters on the x-axis. Then draw another member that starts here and ends at 12. You can click here on Fit World on Screen to see everything centered on the screen. This is the second way of doing it. Again, I'm gonna click on the select cursor mode and delete everything. I'm gonna deactivate the grid and show you the third way of doing this. We can click here on keyboard mode and insert nodes. Can tell the program I want the first node to be at 0, 0. There you have it. The second one will be at 6, and the third one will be at 12. And then remove the keyboard mode and just click on Insert Members and connect the members between the nodes. This is the first segment and this here is the second segment. This is the third way of doing it. The fourth way of doing it is to actually click on the keyboard mode and then go to the Insert Member, and here you can directly insert your beam segments by specifying the start and end nodes. For example, I'm going to tell the program that my first beam segment is between 0, 0 and 6 and 0. See how we drew here a first segment directly. Then the second segment, I just need to click here OK, because you can see that the program has created an equal increment automatically. The first one was from 0 to 6, so the program automatically showed here 6 to 12, and if you click OK it will show you 12 to 18 and so on. So I just need 2, so I'm just going to click here again, and there you have it. These are your 2 beam segments making a beam that is 12 meters long. Next, I will define the material parameters that I am using through the material properties. Then the moment of inertia through the section properties. I'm going to define the 2 types of supports using the support conditions, and I'm going to go here to define my nodal force at midspan. So if we click here on the material properties and come here in the data area region, you will have to create a material first and then assign the material properties. You will have to do the same thing for the section. You will have to do the same thing for the load. First you will have to define or create a new material, give it a name and then assign the numbers to it, and then you can assign that material that you created to the members on screen. So I'm going to click here on create a new material. We can give it a name MAT1, and you can select from steel, concrete, aluminum, or generic isotropic. I'm just going to say generic isotropic, and add here the value of the moment of the modulus of elasticity given to us in question, which is 200 e to the power 3 megapascals. If you remember here, it was given in the question that the modulus of elasticity is 200 gigapascals. Mind your units, please. So I've inserted the modulus of elasticity value here. Next, I can select all the beams on screen and click here on Apply Current Material to Selected Members. The material is now applied to both segments of the beam. We can do the same thing here, but to create the section properties. Again, I'm going to create a new section. I'm going to call it Section 1 and go to Done. I'm just going to use the general properties. You can define a rectangle or an I-shaped beam, T-shaped beam, whatever. But now all the information that is given to us is that the modulus of elasticity is 240 times 10 to the 6 millimeters to the 4. So I'm going to insert that here. Once you have given a name to your section, you can click Done. And the program will ask you for two things here. He will ask you for the cross-sectional area to be used to calculate the axial deformations and the moment of inertia that will be used to calculate the flexural deformations. Now, in this particular problem, we don't have any axial deformations as the beam is not restrained in the x-axis, but one good way of doing this in order to just eliminate the effect of axial deformations is to give the cross-sectional area a number that is really large, number that is huge. So let's say 1 times 10 to the power 12. And then for the moment of inertia, we're just going to insert the actual value given to us in the question, which is 240 times 10 to the 6. So I'm going to add that here. 240 e to the 6. Again, you will have to select all beams on screen and assign this cross-section to them. Next, we will go to supports. The support to the left is a fixed support, so I'm just going to say fixed in the x-axis, fixed in the y-axis, and no rotation. If you do this and select this node here and assign this support condition to that node here, this is exactly what you will get. Now, just to make it look right, I'm just going to add an angle here to have the fixed support similar to the fixed supports that we've been dealing with all the way. If you didn't do this step, nothing will change. A fixed end is a fixed end. And I'm going to tell the program here to reset the support so that I can set the conditions for my roller support that will be here on the right side. Remember that the roller support only prevents translation or movement in the vertical direction, so the x displacement will be free, the rotation on the z-axis will be free, but the displacement in the y direction will be fixed. I'm going to select the node here and tell the program to assign this setup here that I have created to this particular node that I have selected. There you go. Lastly, we will add a nodal load. Again, you will have to define the load, so we're just going to call it load 1. Done. The value of the load, if you remember, is 50 kilonewtons. It is directed in the negative global y direction, and therefore I'm going to come here and tell the program to add a minus 50 kilonewtons to this particular node here. I'm going to tell the program, you see this load, assign this load to the selected node shown on the screen. The next step is to show the results, which can be done by clicking on any one of these four buttons here. The first one is for the axial force diagram, the second is for shear, the third is for moment, and the last one shows the deformed shape of the beam. Before you can see the results, the program will prompt you to save the file. So I'm just going to go to File, Save. I'm going to call the file example1. And now I am ready to see the results. If I click on the axial force diagram, you will see that nothing will happen. The reason for that is the fact that our beam here is not restrained in the x-axis. Although we have a fixed support at A, we have a roller support at B. Roller support does not restrain the x-axis movement, and therefore we will not be having any resistance in the x direction, and therefore the axial force diagram will show nothing. But I like to show on the axial force diagram my reactions. If you click here, you can see that the reaction at the roller is 15.625. If we go to the handmade solution, you can see here by selecting RB as your redundant, you will get 15.625, which is identical to the value shown here by Ftool. That's why I requested the program to show me 3 decimal digits for comparison. Next, I will remove my reactions and draw the shear force diagram, the bending moment diagram, and the deflected shape. I can show the deflected shape with no values and then click on any point on the original shape to show the vertical displacement or deflection at that point. So we can say that at the point underneath the load, which is 50 kilonewton, the deflection at this point here is 1.641 e to the power 1 millimeters, which is 16.41 millimeters or 1.641 centimeter, which is not bad for a beam that is 12 meters long. There you have it. You can actually solve this example by hand and then use the program Ftool to check your solution and acquire a computer skill where you can actually perform structural analysis of a beam using a computer software. Thank you very much for being with me in this session, and best wishes.